Howdy. This is it's not really a Datapack showcase so much as an explanation, because it's going to go into the technical side of one deceptively difficult question. What is RNG? Now, first off, we need to define what an RNG even is. Because I'm sure you've heard the number thrown around, I'm sure you've heard the name thrown around a lot, but there's not a lot of explanation for what it actually is. RNG is short for a random number generator. And what it'll do is every single in-game frame, it will generate a random number up to a certain bound. Now, classically in computing, what they like to do is generate an extremely long decimal number like so. I'm just mashing keys, so this isn't actually random. And suppose you want a number from 1 to 1,000, you would get the last 3 digits. Then you would do it again. With this method, oh, that's the wrong, it's the wrong stick. Oh, it's hard to operate with both of these. Let me put these away for now. With this method, heck, you could probably just keep going along this line and get pseudo-random values until you get all the way up to the top. But this is Minecraft, and there's one very important thing about Minecraft. We cannot easily work with decimals. We can technically store them in storage, but we can't perform operations on them. So, where does that leave us? We need to find a way to use integers to generate random values. And I have with me 6 different methods of doing so. And each of them are going to rely on some formula or some quirk of the game to do something random, or at least something pseudo-random. And I also, pardon me, I'm going to tab over into over into Notepad++. I'll show the code later on in the video when I'm talking about the efficiency of it, but for now I'm just going to tap back and forth. I accidentally generated a graph earlier. Well, I can use that graph to track the progress of these RNG functions as they iterate forward. Without further ado, let's go on to the first option. I'm just going to call it Basic Addition. So with Basic Addition, it's basically what it sounds like. You take a starting number, add something to it every frame, and divide it by something else every frame. Now, in this example, I'm kind of dramatizing it a little bit, because at a passing glance, that seems really good. It's hard to I don't know how you would even be able to track those numbers normally. But let me generate a graph and we'll quickly be able to tell where the problems are. But I've not seen that one before. Just reloaded properly? Nope, it wasn't. Okay, RNG, the generic RNG function for the boss mod might be having a stroke. That's what it's plugged into initially. Anyway, therein lies the problem. It only traces through a certain select number of values. And those values that it skips are based on whatever the additive and the modulus are. In my case, it's 48 and 100. Meaning, from the looks of it, it will skip to every 4th value. Because the highest factor that they share is 4. So that's not very good. Because let me actually grab a piece of outdated technology over in the over in the storage. Let me see if I can find. Yeah, this is. I'm very proud of this, but it has a glaring issue. Notice how the arcs are very. What's the word for it? They're very geometric. If I shoot again, not only do all of them move in the same direction, which is a different issue, they're very geometric. I want them to be fully random, and I can't do that with this method. So let's kill all of those and move on to the. Hell, Pete's sake. I do this every time. Option 1, basic addition. Option 2, prime addition. So, there is another way to do it. Give me a moment to swap these values out so that I can show it off in a moment. So with prime addition, it's the exact same method, but we're using primes instead. And something you may note about primes is that they share no factors. So as you notice, it still seems to follow a sort of rhythm. Just watch when 100 shows up. It's always the same period in between values, but it's definitely better than the old method. Now let me generate another graph real fast. And it does exactly what I was assuming it would. It loops through every single value at least once before returning to previous values. However, the period between each of these values is exactly the same. So let me just pick one of these at random. Yep. It is the exact same time between the first, between it going up once and then going up a second time. Now, pardon me. Let me add a tag onto this so I don't keep killing my. Not you, it would be boss generic graph. There we are. There we go. I'll use that instead. So if you notice, it's very useful and efficient, but it's also not the best method. So we want something that relies on several different numbers, because the more different numbers it relies on, the more likely it is to simulate pure randomness. So that's where option 3 comes in. Option 3 is chambered addition. So what do I mean by chambered? Well, there's 3 different sets of values that all feed into each other. They all have their own unique moduli, which are not changed, but all of the addition happens between each of the 3 values. So this one is tricky to work with, I'll admit. Excuse me for a moment. I need to find all of my variable names. Whatever. I can. Time's a wasting. Let me find these files quickly. There we go. I can just look in it. And yeah, I'll use that. So something to note about these functions is that it doesn't have necessarily an output. Because all three of the values are interchangeable, the value that you use to track can really be, that you can use for operations can really be any of them. I'm going to use operation number 3 because it's the one that I've set to a modulus near 100. But let's graph this real quick. This one is unpredictable, to say the least. So if I run it, it's really good. But you might notice a problem. Not only is it skipping a good chunk of the values, but it's also favoring certain values over other values. So it's more random than before, but not in a good way, because it's more difficult to account for this. Now, I can theoretically fix this a little bit by doing player set at S, RNG EX, chamber 3, set it to 0 and see what happens. Nothing. Let's try the mod. Set the mod to 99. Nothing. Let's try a radical change. 37. Obviously, that shortened the length of it, but as of before, it's the exact same thing. It's very good, very unpredictable, but also certain numbers are sticking out. So the seeds that you use for chamber 1, chamber 2, chamber 3, and their moduli are very, very important. Set it back to, I think it was 100. Yeah, it was 103 before. Oops. All right, there you are. So that's probably my best option so far. Next up is a deceptively bad option. This one is random selection. So the thing with random selection is, let me find output. So that I can show how good this method is. This method is actually fantastic. What it will do is it will generate 100 markers. Give all of them a random ID, and then select one of them at random. This uses the game's internal random function, so it's going to be way, way better than my other options, at least in terms of precision. It's really funny in a way that the more precise, the way that it's defined by our standards, the more precise a function is, the better it is at being random. But it's very, very good. Because no matter what, it will always get a random variable. But let's graph this, and I don't know if you'll be able to tell the issue yet, but it's worth a shit. No, not yet. So at present, it's really good. It's not repeating certain values. It's always getting a random variable. You'll start to see some values kind of creep up. They're never going to creep up too far. So what's the issue? Why do I keep putting on that this is really good but kind of voice? Well, give me a moment to stop the function. Let me plug in some values manually, because for some reason, I'm not entirely sure why. I was originally planning on making it so that it would track these values semi-manually, or semi-automatically. But unfortunately, it doesn't seem like plugging functions, getting the values of how many functions were run, doesn't work when they're called from within functions, so I have to do it manually. But that's not too bad. Do that. And then this is the function that's run every frame. That just ran 503 commands. It is running 503 commands every single frame. That is wholly inefficient. I don't want to use that. I'm absolutely not going to use that. Because think about this. The boat, remember the boat from the Salty Dog video that was quite laggy? Which is strange for how like deceptively simple that boat was. I would be willing to wager that that was around 800 to 900 commands per second. And that involved entities. So that's around our hard limit. So if we're going anywhere near that, there's a problem. Either way, move on to the next one. This is more of a silly one. Because option 5 is in-game time. So my logic here was that if there was a way to track the milliseconds move by very, very quickly. And if you applied a prime modulus to it, it would be really, really hard to track it. That would be a very good pseudo-random number generator. That's all well and good, but there's a bit of an issue with that. Unfortunately, in-game time is tracked in ticks, not in milliseconds, so this is completely pointless. I'm not even going to bother putting it into the graph, because you can probably guess how that goes. It just slowly sweeps across the graph. So that's unfortunate. Funny thing is, though, since it's going off of a scoreboard, it'll continue to increment even when the sign is dead. Option 6, this is the last option that I've implemented, and then I'll discuss a few others that are a bit more finicky that I didn't decide to implement, but they're still worth mentioning. Option number 6 is an optimized variant of the random selection. Because, surprise, the random selection algorithm is terrible, and it's really, really slow. So how do you modify that? Well, before I was creating 100 markers, and that's not efficient. What I can do instead is create 10 markers from 0 to 9, select one at random, then create 10 markers again, select another at random, and then run some math to generate a random two-digit number. Now, this is, as much as I don't like this method, I have to agree, this method is far more efficient. And let me grab the output of this so I can show this off. I think it's this again. Moment. Oh, it's still at select output. Okay, that's perfect. These use the exact same output variable because I'm lazy. They'd never be used interchangeably, so it's not an issue. So, this does almost the exact same thing as the previous version of it, but it's not very detectable from this glance, but it's a lot more efficient. I don't know why, I like looking at graphs like this. Very stimulating. But let's kill those off. Let me do what I did before and run an efficiency thing. Stop that. And then find my variables. Exactly 100 commands, so it's still not great, but that's definitely way better than it used to be. But that is the last of the functions I actually implemented. Because the others, it speaks volumes when the functions that are literally run 500 commands per frame are better than these two, but it's worth mentioning. Option number 7, we'll just like do option number 7 in finger quotes, is a very cool piece of math called the middle square method. Times like this, I'm glad I have a whiteboard because this requires some genuine explanation. So let's suppose that I have some random starting seed. So maybe I do seed of 9. And then 9 squared is 81. 81 becomes the new seed for this algorithm. And then we do 81 squared. Give me a second to plug that into a calculator, because I am not a wizard. 81 squared is equal to 6561. And what we'll do is use 56 as the new output. That says 52. Oops. So 56 will be the new output, and it will continue like this using the previous center values as the new seed, adding zeros to the beginning of the number when necessary to make sure that, suppose you have a number that's 3 digits long. You take 11 squared. Well, 11 squared is 121. That's 3 digits. So you would add a 0, 1, 2, 1, and then take these values. It's a very cool method. Too bad it sucks, fortunately. I really wanted this method to be good, but because it's only using 2-digit numbers, there are at most 99 values that this thing can generate before it loops, and that's the absolute maximum. Odds are it's going to be closer to 40 or 50. And so there are some values that don't work at all. Like, let's use a different seed to start with. Let's use a starting seed of, let's say 40. Seed equals 40, 40 squared equals, what's that, 16? There we go. And then seed is now 60. And small problem, 60 squared is 3600. That results in a loop. Anything that results in, if I recall correctly, it's like 60 or 0 will be infinite loops. We'll just get stuck there. That's only one of a myriad of problems with this method. And there are technically workarounds, but I really don't feel like going through that much trouble for the method when there are better methods that have already worked. And option number 8 is, to a lot of people, it seems like the most logical option. Predicates through Datapacks. Because I've mentioned predicates in the past, but I don't fully understand their functions, but what they are they are special things that are set off by hash marks that can be used as special language by the code. So let's suppose, and you can find some of them in game. Like suppose that you do /kill at e type equals. You might notice there's some of these that have the hash mark. And I think exclamation point is just there because it's in alphabetical order. Yeah. This would kill everything that's an arrow. So it would kill arrows, tridents. I forget if spectral arrows are technically their own entity. I don't think they are. Tipped arrows are, though, so it would work with those as well. It also works with, it's basically roll a die, and if the number is a certain, and if it's above a certain number, do the thing. Now that is very interesting, and it can be very useful, but it doesn't actually output a number. And for examples like the acid crossbow, I need precise numerical values to make this stuff work. So unfortunately, predicates cannot be used. So where does that leave me with the option that I want to use? Basic addition is too predictable. Prime addition is too predictable. Our basic addition is just bad. Random selection takes way too much processing power. In-game time doesn't work at all. Optimized random selection is still good, but takes too much processing power for my liking. And these two are methods that I'm not even considering. So that really just leaves chambered addition. So I was hoping the conclusion of this video would be a bit more fulfilling than that. But actually, I can... What am I doing? I can show off the code. Give me a moment. Bada bing. So this is not the right code to look at. This is. There we go. So for every single bit of code, it runs the same operation. It gets a player holding a snowball, gives it a tag, and from that player's perspective, if they find a snowball, summon an armor stand, set the display to show that current scoreboard, and then kill it, run some operations to do some initialize variables, and then run the function. And then it does that for every single one of these. So let me pull up some of these functions so we can see how in-depth they are. This is basic. It is literally two. It's two functions. That's it. So although it's not very good, it's also the most efficient method by a country mile. Or actually, I think in-game time might be the most efficient, because I think it's actually just one. Yeah, it is just one, because in-game time iterates by itself. So if I was really concerned about efficiency, I could just make this run from 0 to 10 and then go off of that. But I don't know. I like this 0 to 100 because there's more to work with. Let me find the rest. Rhyme. It's also 2. Chambered is actually quite a few. It is 6. And this is the method that I use for the generic iterate RNG function in the boss data pack. 6 variables laid out like so. And then we get to the meat, random selection. We'll pull up all 3 of these. So the first of them, what it'll do is it will run this loop. And both of these run the same loop. And having to find the number of iterations out here to be 100, it'll run 100 times, summon 100 markers, each with their own ID. And it'll keep going until that value is equal to 0. Then it will get 1 sorting by random, this is the baked-in random variable I was talking about before, and store it as the output, and then kill all markers. This is why it runs roughly 500 commands. The optimized variant, which runs about 100, does something a little bit different, where it only goes up to 9, and it'll again go back to the loop and generate 10 markers. Get 1, store its value as A, kill all of them, generate 10 more, get one of them, get their value as B, set a generic constant to 10, multiply B by 10. This is debug text, so don't worry about that. Let me push this aside. And then add A and B together for the final product. it's still quite good, but chambered RNG is faster. I think it's the most efficient and the most precise. So I think I'll close out the video by explaining what I mean exactly by precision and efficiency. So efficiency is basically what it says on the tin. And in our case, it's the number of commands needed. And the other value to consider is precision, which is how random it is. And as we go down the list, we're able to see both. Efficient basic addition has high efficiency but low precision. High efficiency but low precision. Chambered addition is kind of a happy medium between the two. Random selection is very high precision but very low efficiency. Optimized random selection, again, has very, very high precision, but it's also not efficient. And in-game time is the most efficient method by far, but it is terrible. And these two, if I were to implement them, would likely be not very efficient either, because this would have to run a bunch of predicates, and this would have to run an iterating function. But with that being said, I think that's everything I have for this video. Again, thanks so much for tuning in. This is a fascinating project to do. Like, scratched the nerdy side of my brain. I'm not entirely sure what that means, but whatever. It was fun. But that's about it. Have a good day, y'all.